Hello guys, welcome to this new video. So here we're going to go through question 1 in the May 22 time zone 2 paper 2. So here we're given this airboat. We're told it is used for transport across the river, and the boat is moving forwards and air is propelled from the back of the boat by a fan blade. So there's a fan over here pushing air backwards. And in the first part of the question we need to outline why a force acts on the airboat due to the fan blade. Well, as we are told, the fan is spinning, pushing air backwards, so the air is experiencing a force which makes the air accelerate backwards. So air acceleration is going to be backwards, but due to Newton's third law, we know that every force has an equal and opposite reaction force, which means that if the acceleration is experiencing a force, if the air is experiencing a force backwards, then the boat must experience a force forwards, and that's what is going to propel the boat forwards. So what we could say is that due to the spinning, or just due to the blades, air accelerates backwards. And then we know that Newton's third law states that every force has an equal and opposite reaction force. Force has an equal and opposite reaction force. And well, this force is what's going to be pushing the boat in the opposite direction. Something like this. And then in part B, we are told that this boat is tied to the bank with a rope, and the fan is propelling the air at its maximum speed, and we need to show that the mass of about 240 kilogram air moves through the fan every second. Well, we were also given some data at the start of the question, so we know that the radius is 1.8 meters, the maximum speed air can be propelled is 20 meters per second, and we also know the density of the air. And so from these values we somehow need to calculate the mass per second, pretty much. So, well, if we think about what is happening here, in 1 second, some volume of air is going to pass through this fan. So let's say this is 1 second. Maybe this much air goes through the fan in 1 second. Well, if we could calculate this volume, so how much air is going through the fan in 1 second, then because we know the density, then we can convert from volume to mass. And we can actually find the volume pretty easily because we know that these fan blades are cylindrical. So they will have a base which form a circle. If we think about it, this is the boat side over here. Then what we'll see is that the air that moves through the fans in 1 second, this volume will have some shape of a cylinder, as it will just be like a straight line with like a circle as the base and as the top. So that's how much air moves through. And well, we know that in one second, if the air is moving 20 meters per second, then in 1 second they will cover a distance of 20 meters. So we know that this side of the cylinder will be 20 meters. And then this will have some area, which is equal to the area of the fan blades. So we can calculate that since we know the radius. We know the radius is 1.8 meters. And so the area will just be pi r squared. So we can find the volume of this cylinder. So volume of cylinder, well, it's just the base times the height. So the base area times the height, that's how you can calculate the area of a cylinder. So what we need to do is do 20 times pi r squared, 1.8 squared, like this. And this will be approximately 203.58 meters cubed. And now that we know the volume, we know that the density is 1.2 kilogram per meter cubed. We just need to multiply these two so we get the kilograms. So the mass is just density times volume. And so that will just be 1.2 times 203.58. And this will give us 244.3 kilograms, which is indeed approximately 240 kilograms. So like this, we can calculate how much air moves through in 1 second. And then we need to show that the tension in the rope is about 5 kilonewtons. Well, again, we need to remember that the only force acting here is the force by the fan blade. So it's pushing the air backwards. So the force exerted by the fan blades on the air will be equal to the pushing force forwards. And we know that it's stationary, so this rope has some tension in it, which is pulling keeping the boat stationary. So the pushing force is going to have to be equal to this tensional force, because the boat does not move in this direction, so the forces must cancel out. And when we can calculate this pushing force, as we know that this is equal to just the force exerted on the air. And if we remember, there are two ways we can calculate this, as we know that this is the net force, so there's only one force, which is the blades acting on the air, so that's also the net force. And we know that there are two formulas we can use to calculate the net force. There's the well-known Newton's formula, mass times acceleration, and there's also the change in momentum over change in time. And well, here the second formula is going to be a little bit easier to work with, as we know the mass of the air that is moving through in 1 second. This is why we had to calculate this. This is just another typical case where IB uses the keyword show something. If we need to show something, then it always means that we're going to need to use this answer later on in our working out. So this can also be a hint that we can calculate this kilograms per second value. So what we can say is that the change in momentum is just the velocity, or well, we can say the change in mass times velocity divided by the change in time. And well, the velocity is not changing. The air is moving at a constant 20 meters per second. So this will just be the change in mass over change in time times the velocity. And well, we know the change in mass over change in time is just 240 kilograms per second. So we just need to do 240 times the speed of air. So like this. And this will give us 4885 newtons, which is approximately 5 kilonewtons. So here we just use the fact that the net force can be calculated from the change in momentum of the air. So the fan blades produce a change in momentum in the air as they start pushing it. And so like this, we can calculate the force that creates this momentum change in the air. And well, this force is going to be equal to the tension because of this relationship. And then here we are told that the rope is now untied. So now the airboat moves away from the bank, and the variation with t of speed v of the boat is shown in motion. Explain why the airboat has a maximum speed under these conditions. Well, we know that the driving force is constant. So the driving force does not change as the fan blades rotate at a constant speed. It is constant. But as we start moving, the resistive forces will increase. As we can imagine, there must be some frictional force acting backwards, which is not like static friction or dynamic friction. It's just some other type of friction that is due to the interaction of the water molecules and the boat. And that resistive force will change proportionally to velocity. We don't know the relationship with velocity, so we don't know if this frictional force increases linearly or cubically or quadratically with the speed, but we know it increases with speed. And so at some point, this resistive force will be equal to the pushing force. And after that point, there will be no net force, so no more acceleration, so no more change in velocity, and therefore we have a constant speed. So driving force is constant, but we have an increasing resistive force, and after some time they will balance, resulting in F net equals 0, and therefore acceleration is equal to 0, as F net is just m times a. Well, the mass is not 0, so the acceleration must be 0, and therefore constant speed. Like this. And then we need to estimate the distance that the airboat travels to reach its maximum speed. Well, here we need to remember that when we have a velocity time graph, the area underneath the graph will represent distance traveled. So, or the displacement here is the same thing. And well, we can just remember that as the units of the y-axis are meters per second and the units of the x-axis are seconds, and when we calculate area we need to multiply the two units together, as that's how we would calculate the area of a square, for example, of a triangle. And we see that the units seconds cancel out, so we'll just have meters, so the overall units of the area will be meters, and well, that is related to displacement and distance. So there are multiple ways you could calculate the area here. You could try and split it up into some simpler shapes, and then like split it into a trapezium, maybe calculate the area of this with the formula of a trapezium, and then estimate the area of these. Or you could just start counting the number of squares like this, and then calculate that for one square how much distance it travels. So for example, in one square it travels 5 seconds with a speed of 2, so it will be 5 times 2. So in one of these squares it travels 10 meters, and then if you count 54 squares or 51 squares or something like this, then you just multiply these two and you will see how much distance it covered. So both these ways are accepted. So we can say 1 square is equal to 10 meters, and let's say we count 54 squares, then we will find that it traveled 540 meters. And then obviously these like partial squares, you could count like 2 of these as one big square. So for example, this one and this one could be combined to count as 1, and then like this you can calculate the ones on the edge as well. But in the mark scheme there's always like a range given, so if you're like 1 or 2 squares off, it should be fine. Maybe even 3 or 4. And then we need to deduce the mass of the airboat. Well, for this we need a little bit more of creativity. It's kind of hard to see this, I think, immediately. But what we see is that at the start we have constant acceleration. So at the start our gradient is somewhat constant. It's pretty much a straight line. So our slope, if we would draw, it could be fitted with a straight line over here. And well, if we calculate the acceleration here, that's going to be very useful for us, because when our speed is very, very small, this resistive force is going to be very, very small. So just when we start moving, this resistive force will be near 0. That's why our acceleration is constant, which means that the only force acting is this pushing force. And so this can be somewhat considered the net force approximately. And we know that net force is mass times acceleration. So if from the graph we can calculate this initial acceleration, then we can calculate the mass. So because later on this resistive force starts building up, and that's why this curve starts approaching a constant velocity. That's what we just discussed in this part I. So, but when at the start we have no very small resistive forces, we just have this F push, and well, this is just a simple mechanics question. It accelerates the block with some acceleration A, and it has some mass m, and this F would be just m times A. And this A we can calculate from the slope. So we can, for example, take this point. it's at 5 seconds and it's in between 4 and 6 exactly, so unit has a speed of 5. We can take the starting point to be 0, so the initial slope will just be change in y over change in x. So the first coordinate was 5, the other one was 0, and also for the x coordinates. So our acceleration will be 1 meters per second squared, and so we know that F is equal to ma, so m is going to be F divided by a, and our force, well, that was approximately like 5,000, or the more precise value, you can maybe say 4,900 or 4,885, and then we just divide it by 1, and so we get that the mass is 4,885 kilograms. So this was the end of the first question. I hope I was able to help. If you have any questions regarding these solutions, feel free to leave them in the comments, and see you in the next video.